Nice. Okay, so here's what I want to take a quick look at today. Okay, so we want to know if we have, what we're going to start looking at is how do we solve quadratic equations. Okay, now solving linear equations has always been really easy, right? That's been no big deal. If we want to solve something like, 2x plus 3 equals 9, what have we done? Okay, you isolate x, right? And here's kind of a rule that we always have. And it's always been simple in the past, but now things are going to be a little more complicated. We always want to isolate x. If we can point to a single x, we can always isolate it by reversing order of operations, right? And you do that without even thinking about it, because you're so good at algebra, you just know that the two steps in order would be what? Subtract 3, divide by 2. Very good. Okay, so, and really without even knowing it, what you're unconsciously doing there is you've been well trained to reverse order of operations. We know that this is the direction that we go when we're simplifying something, but when we're isolating something, we turn that around. When we're isolating or solving for a variable, we go top to, or bottom to top. So first we add or subtract, in this case subtract 3, then we multiply or divide, in this case divide by 2, right? That gets a little more complicated though when we get into harder equations where we have multiple terms and we don't have a single x that we can point to. For example, if we have something like x squared plus 6x plus 5 equals 0. Oh, that's a bad one. I didn't do the right thing there. Hang on. You have to account for the effects of my cough medicine here today. So let's see. We'll do plus 8. There we go. Okay, better. Okay, so I can't point to a single x there. I've got 2 of them, and I can't combine those. They're not like terms, right? So I can't condense this into a single x value and solve for x. Actually, I can. And I'm going to eventually show you a trick for doing that, but we don't have that in our arsenal yet. So we have to do something else, and you know the answer to this one also. What do we do? Say it again. Okay, I mean, if I subtract 8, and we could try that, that seems reasonable. If I subtract 8 from both sides, though, then I've got x squared plus 6x. There's no way I can isolate that x, right? So that's not a bad idea. Yes, sir?
Well, you could divide 6x by negative 8 divided by 6x, and then you could square root.
Okay, and that's, now Trenton's he's kind of getting at there is a way that we could make this work by completing the square. You guys haven't learned that. It's something I will show you. We could rewrite, we're not going to do that now, but if I could rewrite this as like x plus some number, it's not x plus 4, actually. If I could rewrite this as x plus some number squared plus some other number equals 0, well then I would have a single x that I could isolate and solve, and I could isolate to solve the equation. That's kind of a process though, to get from there down to there. And that's a process we don't know yet. Like I say, it's called completing the square. We'll learn it later. It's not that big for you guys, it'll be nothing. Okay, but short of that, is there I guess let me refine my question just a little bit. Is there a way that we could solve for x here without isolating x? Yes, ma'am? Yeah, we could factor. We could factor and we could use what's called the zero product property. And I think we've kind of gone through this a little bit. Did I ever ask you guys to do a warm-up and do a bunch of multiplication? Yeah. And then you multiply by 0, right? Yeah. So the idea being that if I ever, what the zero product property says, is that a product of two or more factors can only equal zero if one or more of the factors equals zero. The only way I can get a result of zero when I multiply is by multiplying by zero, right? And so if I can break this up into factors whose product is zero, because I have zero on the other side, then I know that the zeros of the function, of the big function, x squared plus 6x plus 8, are going to be the same thing as the zeros of the small factors, right?
Why did plus 5 work?
It didn't work. Why didn't it work? Oh, actually it would have, wouldn't it? Yeah, you're right, it would have. I just didn't want to use a 1 in my answer. Yeah, but you're right, it would have. That's good, you saw that. Now, factoring these kind are pretty simple, aren't they? If I have a coefficient, if a is equal to 1, if the quadratic coefficient is 1, we're just looking for special numbers, and the recipe is pretty simple. I want to find, so to get from here down to here, what's the recipe for finding the special numbers? Two numbers that do what two things? Okay, hang on, are you sure?
No,
Multiplies 8 and adds to 6, right? And here's why. Because all we're doing when we factor, remember, is we are unexpanding, or in this case, unfoiling. So whatever these numbers are, if I were to FOIL them out, I'd get first times first is x squared, plus the outer product, plus the inner product, plus the last, right? That number times that number would have to give me 8 when I FOIL them out. Does that make sense? Okay. So I just need to find those two numbers that multiply to 8 and add to 6. And what are they?
4 and 2.
4 and 2.
Oh, been stating there.
Okay? 4 and 2. Now there are a couple of things we can do here to make this process easier. For one thing, we want to play what I call the sign game. If I know that the two numbers have to multiply to a positive and add to a positive, what do the signs of those two numbers have to be? They have to both be positive, don't they? Okay. So then I know that I'm looking for two positive numbers, in this case 4 and 2. And so what are my zeros then? The -4 and -2, right? Because I know the product of x plus 4 times x plus 2 would equal 0 when one of two things happens. Either this factor has to equal 0, or that factor has to equal 0, right? Because only, multiplying by 0 gives me an answer of 0. So the first one, the factor is 0. Excuse me, when x is -4, or second one would be 0 when x is -2. You guys are good enough algebra students that I don't think that you're going to have to write this step out. I think you can always just ask yourself, okay, what value of x makes this factor 0, right? What value of x makes this factor 0? Even later when we have harder factors that have coefficients of x, you can still do that, right? And what I mean by that is, what if one of my factors, let's skip ahead for just a second. What if one of my factors was something like 3x plus 7? What's the x value that makes that 0? Think in your head, if I set that equal to 0, what are the two steps to isolate x? Say it again. Okay, for this one? Okay, good. And do what then? First subtract 7, divide by 3, right? You can do that in your head though, always. It's always going to be two steps. If I know that this is the factor that I'm setting equal to 0, I'm always just going to add or subtract the constant to the other side and divide by the coefficient of x, right? You can do those mentally. I mean, you guys can. And if you want to write them down, you can, but eventually I'd encourage you not to. Okay, so we found our solutions then, right, by factoring. And that's the whole purpose of factoring, generally, is for us to be able to solve big equations by breaking them into small factors that I can set equal to 0 with the zero product property. Okay? Now we're starting off with chapter 5, in unit 4 with quadratics, which are, have powers of 2 is the biggest we're gonna get in chapter 5. But we're gonna move on in chapter 6 and deal with polynomials where x could be cubed or to the 4th or to the 5th. And we can factor those using techniques also, okay? So this is pretty simple. Let's just get a little bit of practice on this kind. Let's try one more here. If I wanted to factor the expression what if I wanted to factor that quadratic? I'd call that a quadratic trinomial. How come a trinomial? Because it has 3 terms that are being added together, okay? A lot of times books will call that a trinomial. So in this case, the magic numbers, if I'm gonna break this apart into factors, they have to multiply to -20 and add to, okay, let's play the sign game here. If the two numbers have to multiply to a negative, what does that tell you about the signs of the two numbers? Okay, good, they have to be opposites, don't they? Because only a negative and a positive multiply to a negative, right? Now, which one's gonna be bigger? The negative, because the negative ends up winning when I add those together. I get a negative result, right? This is kind of up to you, but I think it's convenient to always put the bigger one first. So we know in our sign game that that's gonna be right. We know that because they add to a negative, the negative cancels the positive with a little bit left over, right? And you even know how much different they are. You know that when you add them up, I get -1. So that means that the negative number must have been 1 bigger than the positive number, right? And so we get -5 and a +4, and we got it, okay? What if this had been a positive? How would that have changed things? Yeah, -4, +5, right? That makes sense? What if this had been what if we'd gotten one like, just tell me how the sign game works for this. What are the signs of the two numbers if they multiply to a positive and add to a negative?
Negative.
Both negative, right? So you see how that helps a little bit, doesn't it? Okay. So no big deal with those. Now it gets a little more complicated. I'm not even going to go through the PowerPoint. I'll put it up on the website if you guys want to look at it for review. But with this group, I don't think I even need to go through it. What happens though if I have something where the coefficient of A is not 0? Okay, let's look at a couple examples. So what if I have, for example, something like, let's start off with this. What if I have I want you to think for a second here. You always catch your breath before you jump into these problems and give yourself a chance to think about it. If I'm trying to solve this by factoring, what would I do first? Cammy's got an idea? No. Say it again? Okay, so we know the template's a good idea. We know that we're gonna get something like this maybe, right? But before we split this apart, is there something else we can do, Kim? Okay, good. So we always want to look for a greatest common factor, right? That's always the easiest way to factor is by factoring out greatest common factors. So is there something that divides into all 3 terms? Yeah, 3, right? Now, when I factor out a greatest common factor, remember that all that really means is I'm undistributing that number. That's kind of the process that you think about. So if I'm gonna undistribute a 3, what am I left with? So I get x squared. Good. Okay, and in this case now, if the problem just asks you to factor completely, I'm not setting it equal to 0, I gotta keep that 3 there, because that is a constant factor. Does that make sense? If the problem is asking me to solve, well, I could just divide both sides by 3 and get rid of it. Does that make sense? Okay. The rule is I can always divide both sides by a constant factor, but I cannot divide both sides by a variable factor. Okay, dividing by a variable means I'm losing solutions. I can't do that. But I could divide both sides by 3. Now I'm going to change this problem in midstream here just a little bit. And I'm going to say that instead of solving in this case, we're just factoring. So that means we got to keep the 3 in there in this case. But once I get to here, now this becomes a pretty easy factoring problem. It becomes one of the factoring problems where I have a 1 in front of the x squared, and those kind are simple. Then I just find numbers that multiply to -6 and add to -1. What are those numbers? Negative, good, I heard it. -3, +2. Piece of cake. So that one was no big deal. Okay, what if we get one though that's a little tougher, where I can't factor something out? So say I get something like this. Okay.
3x plus whatever.
Okay, yeah, these kind are a little tougher, aren't they? Because now I've got to unfoil, I've got to break apart something where I'm going to have numbers with my x's, right? Okay, but this one's not horrible. This one's not horrible because how many convenient factors are there of 3? I mean, there's really only one way to split apart a 3 into a 3 and 1, isn't there? Now, if this leading coefficient were something like a 6 or a 12, yikes, because there's lots of different ways to do that, right? If it was 12, for example, I got 1 and 12, 2 and 6, 3 and 4, lots of ways. But this one, I know that if I unfoil it, I know that the 3x squared, the first times the first when I foil it, has to be a 3x and an x. Does that make sense? If it's going to factor conveniently, and it might not. Now, what about the 10? How many different ways are there to do 10? Now, we know the sign rules here too, don't we? Yeah, it's going to be 5 and 2 or 1 and 10. And I know that if I want these to multiply together to give me a positive and add to give me a positive, I've got pluses there, right? And my candidates are either 10 and 1 or 5 and 2, or I could flip those and go 2 and 5, 1 and 10. And really, one way to do this is just to try them all and see which one works. I would say that if the number of candidates are 4 or less total, that's not a bad way to do it. So in other words, if I only have one set of options for the first terms in the binomials, and the second factor, it's down to 4 or less possibilities, you might even just go by trial and error, just see which one works. If I FOIL these out, we'll just cancel them out as we go. If I FOIL these out, let's try the top ones first. I'm going to get 3x squared plus 3x plus 10x, right? If I FOIL, when I say FOIL, you know what I mean, right? I've got my first times first, so we'll just do this. First times first is 3x squared, outer product would be 3x, 3x times 1 would be 3x. Inner product is 10 times x is 10x. And then last would be 10 times 1 is 10. Does that work? Doesn't work. So we can cancel those guys off, right? And let's go back and try something different. What if I had 5 and 2? So then that would give me outside product would be 3x times 2 is 6x. Inside product would be 5 times x. Does that work? That gives me 11x. Still no good, right? So we can cross those out. What about 2 and 5? Well, let's try that. So if I do 2 and 5, I'm gonna get 3x times 5 is 15x. 2 times x is 2x. Now that worked, didn't it? That gave me my 17x in the middle. And so those are the winners.
What happens to dividing everything?
By what? Yeah, and now in this case I can't because there is no greatest common factor. There's nothing that divides into all those. Right? Does everybody see that? So, and it'd be nice if there were. That would make things easier, but there wasn't this time. So one strategy, if there aren't very many ways to FOIL it, just see which one, trial and error, see which one works. Sometimes that's not a good idea. There are too many things to try. So there's another strategy. Have you ever heard of the strategy A times B then split C, or excuse me, yeah, A times C then split B? I'm gonna show you. This is a good one. So the other thing we could do is we could look at, to see if this works, what are the values of A, B, and C in this trinomial? Okay, so A is 3, B is 17, C is 10. So the product of A times C is what? 30. Okay, so AC equals 30. And we're just gonna look for numbers that multiply to that number, to A times C, to that product. So two numbers that multiply to 30 and add to 15B. That's easier to see, isn't it? Right? We know that if the numbers have to multiply to 30 and add to 17, they're both positive. And I want you to notice a trend here. If we look at the possibilities, products of 30 are gonna be 30 and 1, 15 and 2. As these get smaller and these get bigger, then we get what, 5 times 3? And then we flip it over and go 3 times 5, but that's not really accomplishing anything, right? Because we're gonna get,
Yeah.
oh, I'm sorry, 5 times 6. 5 times 6. Did I miss any? Oh, 10 times 3. 10 times 3, 6 times 5. Did I miss any now? I think I got it, okay? I want you to notice something. These are the products that multiply to 30. Let's look at their sums, at the corresponding sums. So in this other column over here, we're gonna do the sum of the two numbers. 30 plus 1 is, so that one didn't work, right? 15 plus 2 is 17, 10 plus 3 is 13, 6 plus 5 is 11. Do you notice a trend there? As the numbers are further apart that I'm multiplying, their sum is always going to be bigger. Yeah, as the two numbers get closer together, as they converge, their sum gets smaller, right? Does that make sense? Now, there's a pictorial model for that. This is kind of cool. If you think about this, if I take the product of two numbers, isn't that like calculating the area of a rectangle, right? And so if you think about this, the area, I either have a long skinny rectangle or a very squarish rectangle when I go from 30 by 1 to 6 by 5. The areas are the same, but what I'm calculating when I calculate the sum is really just half of the perimeter, right? Shouldn't the perimeter be smaller and more efficient for a more squarish shape than for a long angular or for a long drawn out rectangle? Right, you'd have to walk fewer steps to walk around this perimeter than you would this great big long stretched out one, right? That's just intuitive. That makes sense to us, doesn't it? If we're gonna enclose the same area, it's more efficient to enclose it in a square than a big stretched out rectangle. And so it makes sense that this trend would exist, right? But we know then, why do I bring this up? Okay, I bring this up because if we've got some enormous number over here, if A times C is a really big number, and we're hunting for magic numbers that multiply to AC and add to some number, well, we know that if this is a really long list, and we start up here near the top where the numbers are really, really different, and it's way too big, we could skip down the list to where they're more similar, right? We know that the numbers are gonna get smaller as I go in that direction. And so if the numbers I'm choosing are all way too big, skip down the list a little bit to where they're closer together to get a smaller result. Make sense? Okay, so but let's finish this up then. How does this work? So we found our numbers, right? We found that, that here's the winner. 15 and 2 multiply to 30 and add to 17. So what do we do with that? Okay, well, we take the original equation, 3x squared plus 15x plus 30. Oh, 17, sorry. 17. And we're gonna factor this by grouping. We're gonna split the middle term, because remember what it said was A times C then split B. So if the magic numbers are 15 and 2, we're gonna take, all right, thank you. Just dump them right over there. How about the other side of the chair? Thank you. So if the magic numbers are 15 and 2, then we're gonna split that 17x up, thank you. That 17x up into a 15x plus a 2x, or vice versa. It doesn't make any difference the order. Okay, so everybody get this. Jennifer, turn around, you gotta really watch this part. This is tricky. So this is gonna become 3x squared plus 15x plus 2x, or 2x plus 15x. Doesn't matter. We'll just arbitrarily pick it that way. Doesn't matter, it's gonna work either way. And then we're gonna go through a process called factoring by grouping. Once we've written this out as 4 terms, we've split that middle term into 2 terms. So I now have an even number of terms. I can factor by grouping. I can take the first 2 terms together in one group and the second 2 terms together in the second group. And I'll do this process. I'll take the first group and focus on them. Let's factor out the greatest common factor. What's the greatest common factor of 3x squared and 15x? What is it? 3x, not x squared. I can only take an x out because this one only has an x to give. I can undistribute a 3x. So my greatest common factor is 3x. And that gives me a leftover factor of what? If I undistribute that. So 3x times what would give me 3x squared? X plus 5. Yeah, that makes sense, right? Factoring means dividing. It's like I'm dividing away. What's 3x squared divided by 3x? Well, if I did that, 3x squared divided by 3x, the 3's would cancel and one of the x's would cancel and I'd be left with an x, right? 15x divided by 3x would be 5, okay? So however you want to think about it, undistributing or dividing by that greatest common factor, either way. So that's what we get from the first group, plus, now here's what's really cool about this. If my search for the magic numbers was successful, if I was able to find 2 numbers that multiplied to AC and added to B, factoring by grouping is guaranteed to work, has to. So I know that the second group has to give me the same pattern. I have to get a greatest common factor and a leftover. And here's the key. The leftover factors have to be the same. So I can automatically write in an x plus 5 over here, and the only thing I have to answer then is, what's the greatest common factor that causes that to happen? 2. Yeah, exactly. Okay. And so my answer then, yeah, this is pretty cool, isn't it? So my answer then is just going to be, if I've got, now I want you to think about this. In fact, I'm going to take this to the next page. So if I've got, Okay, so if I've got that result, how many terms are there?
In each.
I wanna know just on a big level there, how many terms are there? How many things are being added together? Okay, but now you're burying yourself too far. I mean, at an outside level, I've got how many things being added together? 2, yeah. I've got this thing over here being added to that thing over there, right? Now, how many factors are in the first term? I'm seeing some 2s, yeah. I've got a 3x being multiplied by an x plus 5. Terms, the best definition I can think of for terms are things that are being added or subtracted. The best definition for factor is things that are being multiplied, right? So I have 2 factors in the first term and 2 factors in the second term. Do you see any like factors, any common factors? Well, yeah, the x plus 5s. The leftover factors are always going to be the common ones. And so I could undistribute an x plus 5 out of each of those 2 terms, couldn't I? And so we're left with x plus 5 times what's left over. Well, I'm going to have a 3x plus, oops, supposed to be red, plus a 2, right? And I got a factor. See how that worked? So my result then is x plus 5 times 3x plus 2, right? Okay, let's try another one of those. Now let's try to put all those steps together. So let's try another one of those. Okay, how about, factor that. Always look for a greatest common factor first, because that always makes things easier if I can factor something out. Can I? No, not in this case. I can't factor anything out, so we gotta look for the magic numbers. We gotta do our search, A times C, then split B, right? So what's the product of A and C here? So they have to multiply to AC, which is 72, and add to what? 18. So I'm looking at numbers that multiply to 72 and add to 18, okay? And to do that, we'll just look at our factors. Now, what are the signs going to be in my numbers? Both positive. So I get 72 times 1, 36 times 2. Let's see, 3 goes into that, so it'd be what, 3 and 24? 4 goes into that, and 18. 5 doesn't go into that, but 6 does. 12 and 6. And have we found any?
Yeah.
12 and 6 works, doesn't it? Right. And look at the sums of these. These are way too big. That sum is 73, 38. We got to go way down the list to get to 18, don't we? Well, finally we get to 18 right there. So that's our winner, 12 and 6. Agreed? So I'm just going to split up my 18x into a 12x and a 6x. Right, so I get 8x squared plus 12x plus 6x plus 9. Now, my advice is start building a template. You know that we got to break this up into 2 groups. Well, we already have our 2 groups. 8x squared plus 12x plus the quantity 6x plus 9. Now we know that this is our steps in order. Pretty simple. We're going to focus on the first group, split it apart into a greatest common factor and a leftover. We know that the second group has to have the same leftover, so we just got to figure out what's the greatest common factor that goes with it, and we're done, right? So we can do this. Before we do any work, we know that the pattern has to be, oops, has to be this, doesn't it? Right? So what's the red greatest common factor from the first one? So what's the blue leftover? Because we're just dividing, aren't we, right? So then we know this has to be, once we get there, we know that this one has to be a 2x plus 3. So the question is, what goes out front? 3. So what's our answer? You can really do it in one step now, but if I undistribute or factor out the common leftover factor, pull that out in front. What am I left over with? Yeah, I get 4x plus 3. See it? That's pretty cool, isn't it? That it works like that. And the whole key on this is, you don't have to do all this work if you can't find the magic numbers. Because if you can't find the magic numbers, factoring by grouping won't work. And we'll have to move to plan B, which I haven't showed you yet. But, right? So in this case, all we can do with up to this assignment, these are your options. Are we getting pretty close to the end here? Yep. 8 minutes. Okay, so up to this point, I'm going to give you an assignment that's going to have you just practice some factoring. It's going to ask you to do 2 things. It's going to ask you to factor quadratic expressions completely, okay, which is what we've been doing. And then honestly, an easier thing to do would just be to solve. If I say solve the equation by factoring, the only difference would have been that that whole thing would have been equal to 0, right? If the whole thing is equal to 0, then my factored version is equal to 0, and what's the extra step? Now I've got it factored. Apply the zeros. Yeah. Now that we got it factored, we'll just apply the zero product property. So if this had been the original question, solve this thing, what's going to be the 0 of the first factor? If I set it equal to 0 and solve, well, if 2x plus 3 equals 0, what are the 2 steps to get the x by itself? Subtract 3 and divide by 2, so negative 3/2, right? Or, what about this one? What do I do here? Okay, good. Subtract 3, so negative 3 divided by 4. Right? You get the idea? Okay, and so your answers are always going to be either, you're going to, if you're just factoring, you would enter those 2 factors. Do you suppose order makes any difference in the answer? No, doesn't make any difference. Makes no difference at all. Multiplication is commutative, so you could enter those in either order. If it's asking you to solve the equation, you would just list the 2 solutions, and you've done stuff like that. The other possibility is at this point, cannot be factored. Okay? And that's, so if you're trying to factor something and there aren't magic numbers, at this point you just say does not factor. How do we solve those kinds of equations instead? Well, I mean, we'll get to that. That's kind of the next step. Okay? Does that make sense though? You gotta go? Yeah. All right.